Good day everyone. My name is Jose Miguel Cervantes and I'm going to present the work Superficial Absorption of Germanium on 001 Lithium Lanthanum Titanium Surfaces. Abstract and Introduction. High specific capacity of germanium, 1600 mAh per gram, makes it an essential anodic material for increasing the energy storage in the lithium-ion batteries. With liquid electrolytes generate exothermic chemical reaction and a solid electrolyte interface 1 which decreases drastically the germanium anodic capacity. Figure 1. Lithium lanthanum titanium peroxide are potential solid-state electrolytes for lithium-ion batteries because they offer good chemical, electrochemical, and thermodynamic stability at the electrode-electrolyte interface. Besides, their ionic conductivity is comparable with that offered by other liquid electrolytes such as lithium hexafluorophosphate. Thus, in this work, the compatibility of those materials was studied through electronic structure calculation using LDA plus U density functional theory. The model consists of the germanium atoms absorbed on a lithium lanthanum titanium peroxide surface. After structural relaxation, germanium atoms sought to interact with oxygen atoms regardless of the initial site where they were placed. Through electronic density difference analysis and partial density of the electronic states, the formation of covalent bonds between germanium and oxygen atoms is observed. This was consist with the absorption energy obtained 6.7 electron volts. This result showed that lithium lanthanum titanium electrolytes with a lithium oxide termination could form a chemical stable electrode-electrolyte interface with germanium. Model. As can be seen in Figure 2a, on the lanthanum titanate surface with a titanium dioxide termination, germanium atoms were placed at different absorption types, labeled as titanium top, oxygen top, hollow oxide valley, bridge 1 and bridge 2. Likewise, on the surface with a lithium oxide termination, germanium atoms were placed in the lithium top, oxygen top, bridge 1 and bridge 2 absorption types. Figure 2d. Calculation scheme. Electronic properties and chemical stability and the electrode-electrolyte interface were studied by means of difficult calculation in the LDA plus U approximation, with the CAPC functional as implemented in the casted cut. Ultrasoft pseudopotential were used with a cutoff of 440 electron volts and 4x4x1 Morcos pack grid. Results. As can be seen in Figure 3, the covalence is confirmed by the partial density of the electronic state of the first monolayer with absorbed germanium. From A to F, for the case of the titanium dioxide termination, there are strong hybridization between the germanium p and titanium d orbitals and the titanium top sides. For the oxygen top and hollow sides, there are strong hybridization between the germanium p and titanium d orbitals, as well as germanium p and oxygen p. Finally, for the oxygen valley bridge 1 and bridge 2 sides, there are strong hybridization between the germanium p and titanium d orbitals, with the interaction between the germanium p and oxygen p orbitals having a less covalent character. From G to J, for lithium oxide termination, in all cases there are hybridization between the p orbitals of germanium and oxygen. Figure 4 shows the electronic density difference. It shows the charge transfer between the surface of the electrolyte and the absorbed germanium. The violet and yellow surface indicate a positive and negative difference respectively. From A to F, for lithium titanium dioxide termination case, After geometric optimization, the germanium atom moved to another absorption site except for the titanium top case. For the oxygen top and hollow cases, the germanium sought to interact with two oxygen and one titanium. For the other cases, the germanium seeks to interact with two titanium atoms and one oxygen. In all cases, since there is an accumulation of a positive electronic difference between the surface and absorbed germanium atom, the formation of germanium-titanium and germanium-oxygen covalent bonds can be observed, in agreement with the results obtained in the partial density of the electronic states. From G to J, for the case of the lithium oxide termination, after the geometric optimization, the germanium was moved seeking to interact with two oxygen atoms in all cases. Again, charge transfer suggests the formation of germanium oxide covalent bonds. Figure 5 shows the absorption energy, which indicates how adherent the germanium is to the surface of the substrate in the different cases studied. For the leaf-free perovskite with titanium dioxide termination, the germanium is more strongly bound at the oxygen top site. However, the germanium remains more strongly attached to the lithium oxide termination than in the case of the titanium dioxide surface. In figure 6a, it's observed by calculating the grand potential that the most thermodynamical favorable surface is the one where germanium is initially placed at the oxygen top side for the case of the titanium dioxide termination. For the case of the titanium oxide termination, figure 6b, we find that all structures obtained after structural relaxation have the same probability of forming. Conclusions. For the lithium dioxide termination, when the germanium is absorbed on the titanium top side, there is a charge gain in the titanium-germanium bond. In the other cases, germanium oxide and germanium-titanium covalent bonds are formed. Likewise, for lithium atom titanium surface, germanium atoms sought to interact with the oxygen atoms, forming germanium oxide covalent bonds. Figure 3 and Figure 4. For the titanium dioxide termination, the most thermodynamical stable surface is the one where the germanium atom is at the oxygen top side, and for the lithium oxide termination in all relaxed structure is the same. Figure 6. Absorption energy indicates that germanium is more strongly attached to the lithium oxide termination. Figure 5. Lithium natanotitanium electrolytes with a lithium oxide termination will form a chemical more stable electrode-electrolyte interface than using a lanthanum-titanium electrolytes with a titanium dioxide termination. Reference and acknowledgements. Thanks very much for watching.